Hi there, thanks for clicking on and watching. Welcome to this video. Hopefully you've done so because you are studying maths at A level. This video is going to be all about the lower six, the AS pure content covering the logs and exponentials chapter. So either you've already studied this and you want to revise, or you just want to get a head start and have a little look and find out what logs are. So that's exactly what we're going to do in this video. So let's get started. Here are all the particular topics that are included in this video, and if you wanted to skip one of them and just look at one in particular, then go to the description where you'll find the timestamps and you'll be able to just click on that and go directly to that particular topic. So let's have a look at plotting some exponential graphs. They're all going to have the same shape. If you've heard of exponential growth, it doesn't grow in a straight line. It rapidly grows as the x values get bigger. But let's have a look at a simple exponential graph. 2 to the x. It's an exponential function because the variable x is in the exponent, it's in the power position. So let's look at some values in this table. So from x going from -2, -1, 0, 1, 2, 3, and then what are the y values? Well, when x is 0, 2 to the 0, anything to the 0 is 1, 2 to the 1 is going to be 2, 2 squared is 4, 2 cubed is 8. What about when x is minus? 2 to the -1, a minus in a power just means it is underneath, so it's going to be a half. 2 to the -2 means 1 over 2 squared, which is a quarter. So you can see that none of the y values are going to be negative, even when x is negative, because x in the power just means that it's going to be underneath. So they're all going to be this basic shape here. They're all going to go through that one. Let's have a look at another one. Y equals 3 to the x, and do a similar table between the same values. So when x is 0 again, 3 to the 0 is going to be 1, 3 to the 1 is 3, 3 squared 9, 3 cubed 27, 3 to the -1 will be a third, and 3 to the -2 will be a ninth. So as this number in the base has got bigger, we can see it's more rapidly growing once we've got past the y-axis, but here these will be lower. So it's going to start underneath, go through the same point at 1, and then rise more steeply. What about y equals half to the x? So this is really the same as 2 to the -1 to the x, and then using our powers of indices, you can times them together. That's really 2 to the 1 times -1 times x, which is just going to be -x. Now thinking about our transformations of graphs, when we've got the shape of the graph, the 2 to the x gave us the shape, but when we've got this minus here, we've made the x value, the variable, negative before we've given it its shape. So this is going to be a transformation that is the reflection in the y-axis. But let's have a look at some values and see how this is going to take shape. So again, starting with the 0, 2 to the 0 again is going to be 1. When x is 1, 2 to the -1 is going to be a half, 2 to the -2 a quarter, 2 to the -3 is an eighth, and then 2 to the -1 will be 2, 2 to the -2 will be 4. So you can see how we're going to get that reflection because it's going to do this. So that is y equals 2 to the -x. So we've had a look at y equals 2 to the x and y equals 3 to the x. All exponential functions have the same shape. They all go through 1 there on the y-axis, but there is a function somewhere between these two, which is y equals e to the x. and this is a special exponential function. It's called the exponential function. Now E stands for the number 2.718281828. That's just the start of it because it goes on and on and on. It is an irrational number, and that is why we have the symbol E. So it was first thought about in the 17th century by Jacob Bernoulli in terms of compound interest, but then it was Euler who proved that it is actually irrational. So lots of irrational numbers come in terms of shapes. You've got pi is equal to circumference divided by diameter, but E is based on rates of change and growth. So we'll have a little look about where that came from in a minute. But if we just look at these three graphs here, E is special because it is the one function that if we plotted the gradient of this line at any point along the line, it actually maps onto itself. If we plotted the gradient of the line y equals 2 to the x, so the slope here is slightly, if that's the value of the function there, the actual gradient is slightly behind. You can see that all the lines are going to be increasing, so the gradient is increasing, but the gradient of 2 to the x is slightly behind the function, and 3 to the x, the gradient is slightly in front of the function. It's growing rapidly, but e to the x, it's the one function that it actually maps onto itself. So what do we do when we're finding the gradient? We integrate. So I just draw it by itself here. Y equals e to the x. So if we had e itself, e to the 1, so that's the number 2.71, this number here. If I actually found the gradient at that point, the gradient would also be e. But not only that, if I wanted to find the area under the curve, then that would also be e. So in terms of doing some maths, and when we're differentiating, when we integrate, we're using calculus, it's really easy if we've got our exponential function in terms of base e. It's going to be really easy to calculate the gradient and the area under that curve. E is known as Euler's number, as it was Euler who first proved that it was an irrational number. Now, it's said that he did not name it after himself using the letter E, but it is kind of nice that it has the letter E. It's just that he'd already used A, B, C and D for something else. Other irrational numbers such as pi are based on geometry of a circle, but E is based on rates of change and growth. Now, it was first thought about in terms of compound interest, though. Another mathematician, Jacob Bernoulli, in the 17th century, he discovered that if we think about compound interest, if we had £1 and we left it in the bank and the bank gave us 100% interest, at the end of the year, we would have £2. What if they decided to give us 50% halfway through the year? So we'd have £1.50, and then based on the £1.50, give us another 50%. So 75 pence added on would give us £2.25. And you might think if we take smaller increments more often, then this number here would just keep growing. But what if I had my £1 and I added a 12th on and did it 12 times a year? So I'd be timesing by 1 plus 1/12 and doing it 12 times, so raising to the power 12, out would come £2.61. Now what if I did it daily? So just added on 1/365 and did it every day for a year, out would come £2.71. So you can see that even doing it daily, I'm now getting a number that is like E. And Jacob Bernoulli discovered that if I do this and just use a formula, so 1/n to the n, and as n gets larger, this tends towards this number e. So it's no surprise when we look at the graph of the exponential function y equals e to the x, then the rate at which it is growing exactly maps on to the actual function itself. So y equals e to the x has this really special property that when we differentiate, it just maps onto itself, so it is just the same function. But what if we have y equals e to the 2x? We've got a 2 in front. Well, whenever there's two things going on, you use the chain rule. So you have to decide what's the inside function and what's the outside function. Whatever happens to x first, that is going to be the inside function, and whatever happens second, then that is the outside function. Now, using the chain rule, what you do is you differentiate with respect to the outside and leave alone on the inside. So just pretend this 2x is just e to the x. Then how would we differentiate? It would just be itself, so we leave alone on the inside. Now, because this wasn't just e to the x, it was e to the 2x, we then have to multiply by the differential of the inside function. So that's going to be times by 2. So it's going to be 2 e to the 2x, and that is how you differentiate. If y equals e to the kx, then dy by dx is just going to be k e to the kx. So when we're transforming graphs, there are 6 different ways we can do that, and they come in 3 pairs. I like to think of them as after and before. So we can make transformations, we can add or subtract. So if we had a function and then added a constant, we can do that after we've got the function, or we can add the constant before. We can multiply and divide. So we've got the function and then times it by a constant, or we can times those input values by a constant and then apply the function, or we can make the function negative or make the input values negative and then apply the function. So if you can remember them like this in pairs, then the ones that are applied after, they affect the y coordinates and they go the way you think. So if you're plotting the function and then you add a before you plot that y value, then it's going to move the graph up a places. If you add the a and then do it before, all the ones that affect the before affect the x coordinates, and they go a little bit the opposite way to the after ones and go the opposite way than what you would think. So adding this a lifts the graph up and down. Adding this a before, it's going to move the graph to the left by a. If we're timesing by a on the front, this is a stretch. It's parallel to the y-axis, all y coords times by a. So if you can remember the after, then the before one, this is similar. It's a stretch parallel to the x-axis. Now here's how it goes different. All the x coords times by 1 over a. So these before ones always go a little bit the way you don't think, as opposed to the after ones. Then the negative ones, making it minus before we apply the function, that is going to be a reflection in the y-axis, and making it negative after we've applied the function, that's a reflection in the x-axis. So let's have a little look what these transformations do in terms of the exponential graphs. If we've got y equals e to the x, I've plotted on all the graphs here, but what have we done? Y equals 3 to the x. This is a transformation. It is timesing it by 3 before the graph has got its shape. So this is a stretch parallel to the x-axis. All the x coordinates are going to times by 1 over 3. So it's going to be a sort of squash in this way, and it's going to come from underneath and go like that. Now it's still going to go through this place here because when x is 0, timesing it by 3, it's still going to be 0, so e to the 0 is going to be 1. Now if we want to differentiate this, dy by dx using the chain rule is 3e to the 3x. The next one, y equals 5e to the minus x. So this minus here is this one, and it's a reflection in the y-axis. So if I was to draw y equals e to the minus x, that would be that graph there, and then multiplying it by 5 is this type. It's a stretch parallel to the y-axis. All the y coordinates are going to times by 5, so it's going to come up and go through 5. So it's going to be steeper. It's going to come down, and again it's going to approach the x-axis, but the x-axis is an asymptote. If we want to differentiate that one, then the 5 is just going to join in, the minus is going to come down, so it'll be minus 5e to the minus x. This last one, this third here, is this transformation again, but all the x coordinates are going to times by 3, so it's going to be a stretch that way in the x direction, and this 2 is this one, the whole graph is going to shift up by 2. Now the asymptote is here, is the x-axis. This is the point 1, but the asymptote is going to also shift up. So that's the line y equals 2 is an asymptote. And then we're going to have the graph shifting out. So it's going to go something like that. And then if we want to differentiate that one, that will be the 2 will go out and we'll have a third e to the third x. So here's an example where we're modelling, and this is an example from the textbook. We've got the density of pesticide in a given field is this exponential equation here, where t is time in days since the pesticide was applied. So for part A, estimate the density of pesticide after 15 days. Well, that's when t is equal to 15. P will equal 160 times e to the 0.006 times 15, which comes out to be 145.2. So that will be milligrams per meters squared. In B, interpret the meaning of the 160. So when t is equal to 0, P is equal to 160. And that will be milligrams per meter squared. And this is the initial amount of pesticide applied. C, show that dp by dt is kp. So dp by dt, we're going to differentiate. So the 160 is going to join in, the minus 0.006 will come down, so it'll be minus 0.006 times 160 e to the minus 0.006t, which is equal to minus 0.006 p. So k is equal to 0.006. And if you work that out, dp by dt is minus 0.96 e to the minus 0.006 t. Part D, interpret the significance of your sign. It is negative, so negative meaning the density is decreasing, which you would expect. And then part E, sketch the graph. Well, when you're doing this sketch and you're modelling, you're just really looking from when t is equal to 0. This is t, so we've got this 160, and it's coming down because it's exponentially negative, so that would be our graph. Writing log equations and using logarithms, logs are just the inverse of exponents. So if I was to write 4 cubed, that's equal to 64. If I was to write that in terms of logs, log to base 4 of 64 is equal to 3. So here you've got base 4 and you've got the power, or the exponent, is equal to 3. Here the base is 4 and the answer to that log equation is the power. So it's this pattern here that 4 cubed is equal to the 64. Now, there are 3 rules that you need to learn backwards and forwards, and I'm going to explain them in terms of base 2. So if I've got log to base 2 of 8 plus log to base 2 of 4, log to base 2 of 8 is saying what power do I need to raise 2 to get to the 8. So that's just another way of saying the number 3, because 2 cubed is 8. And what power do I need to raise 2 to get 4? It is 2. So writing those that sum in terms of logs is just saying what is 3 plus 2, and the answer to that is 5. So in terms of logs, log to base 2 of 32. 2 to the power 5 is 32, so that's just writing 5 in terms of log to base 2. So the rule is here, if we've got log to base a of b plus log to base a of c, you have to times the numbers together, log to base a of bc. You can see here that the 8 times by the 4 gives you that 32. So that is rule number 1, that if you are adding and the logs are in the same base, you just multiply the numbers together. Now this ties in with the rules that we've got for exponents, for powers. If you've got 2 cubed times 2 squared, you add the powers, and that's 2 to the power 5. Here, if you are adding the logs, then you multiply the numbers there. Right, rule number 2 is when we take away logs. So if I've got log to base 2 of 32 and I take away log to base 2 of 8, that is just saying 5 take away 3, which is 2, and that's log to base 2 of 4. Now because we're taking away the logs, you can see 32 and then divide by 8 gives you that 4. So rule 2 in terms of generally, log to base a of b, take away log to base a of c, you divide those numbers, log to base a of b over c. Now the third rule, if I've got log to base 2 of 4 and I add on exactly the same thing, another log to base 2 of 4, by rule number 1 I've got log to base 2 of 16. But because I'm adding the same thing, I've got 2 log to base 2 of 4. Now the relationship here is that this number on the front comes up as a power, because that's the same as log to base 2 of 4 squared, which is our log to base 2 of 16. So if we've got k log to base a of b, then that number on the front just comes up and it's the same as log to base a of b to the k. Let's have a little practice of writing some log equations. If I've got log to base 5 of 25, then the answer to that will be 2. 5 to what power gives you 25? The answer to the log is the power. Log to base 3 of 27. 3 to what power gives you 27? That will be 3. Log to base 2 of a quarter. Well, a quarter is 1 over 2 squared, which is 2 to the minus 2. So 2 has to be raised to the power minus 2 to give us a quarter. Now we think about the graphs. all our exponential graphs were all this shape going through here at 1, and log functions are all the inverse operations. So where the exponential function doesn't go through the x-axis is an asymptote, then inverse functions are a reflection in the line y equals x. So your log graphs are going to come up and do this and be a reflection in that line diagonally across the page, and here that's going to be 1. So you can have the answer to the log being negative, but you cannot take the log of anything negative. The log graph doesn't go and is invalid for any negative x values. Now over here, these are the 3 buttons on your calculator. When I was at school, we didn't have the top one, we only had the bottom 2. But here you can feed in on your calculator log to any base. When it's ln here, this is shorthand for log to base e, so we just write that as ln. So that's when we're in base e. So where e to the x is the exponential function, then ln of x is the natural log graph, and that's going to be the inverse of y to the x. And here, when you've just got log written on its own, there's a button on your calculator that is going to be always log to base 10. Let's have a practice of using our rules. Because these are to the same base, then we can use that addition. What you've got to do is times those numbers. So writing it as a single log will be log to base 3 of 42. B, same log, so we just need to divide the numbers. So it's log to base 2 of 5. 15 divided by 3 is 5. C, it's a bit like BIDMAS. Logs have their own order of operation. So before you can apply the first 2 rules, you must just start with log. So this 2 we're going to have to take up, and that 3 using that rule number 3. So this is log to base 5 of 3 squared, which is 9, plus log to base 5 of 2 cubed, which is 8. And then you can use rule 1 and times them together. It's log to base 5 of 72. Then D, again, you've got to move that up first. Log to base 10 of 3, take away log to base 10 of a half all to the 4, which is going to be 1/16. And then because it's take away, you're going to divide. 3 divided by 1/16 is the same as 3 times 16. So that's going to be log to base 10 of 48. Doing the other side, doing the same thing with the letters. In terms of logs, we've got to now work and use the rules and go backwards. So this is 2 log to base a of x plus log to base a of y plus 3 log to base a of z. So writing them all as single logs. That 2, when you separate them all with a plus, because all of these are times together, and then the 2's and the 3's are going to go down on the front. B, we're going to have log to base a of x, take away 3 log to base a of y. C, you're going to have log to base a of x plus half log to base a of y minus log to base a of z. And then D, log to base a of x minus 4 log to base a of a. And a to what power gives it itself is just 1. So log to the base a of a, if these letters are the same, that's always going to be 1. So this is log to base a of x minus 4 times 1, which is 4. So here's an exam question. You can pause the video and have a go to test your understanding, or just continue to watch. I'm going to go through it now. So we've got the population P of bacteria is given by this formula where T is the time after the experiment has begun. So find the bacteria after 7 hours. That will be when T is equal to 7. So P will be 100 e to the 0.4 times 7, which on your calculator comes out to be 1644.46. So 3 significant figures, 1640. Part B, interpret the meaning of the constant. Well, always those numbers on the front are when T is equal to 0. P will just equal 100 because anything to the 0 is going to be 1, so we'll just be left with 100. So this is the initial amount of bacteria. So just 1 mark for getting that. And then part C, how many whole hours after the experiment does the population of bacteria first exceed 1 million? So we need to be bigger than 1 million with our bacteria, which is modelled by the equation 100 e to the 0.4 t. So we need to unravel and solve this inequality. First of all, you would divide by 100, so that would leave you with 10,000 being less than e to the 0.4 t. Now, whenever you've got the unknown in the power, what you do is take logs, and because we are base e, we're going to take the ln's to both sides. So the ln of 10,000 has to be less than 0.4 t. If you do the ln of 10,000 divided by 0.4, that has to be less than t, and that is 23.025 has to be less than t, so t is equal to 24. So after 24 hours, the bacteria in the experiment will exceed 1 million, and you can put the 24 into the formula and you will see that that is the first time P goes bigger than 1 million. Here's another exam question to have a go at, so you can pause the video, test your understanding, or just keep watching. I'm going to go through it now. So we've got this equation, and noticing that it's both terms in terms of base 3, and we've got a takeaway. So writing that as a single log, you can have log to base 3 of 3b plus 1 all over a minus 2 is equal to minus 1, and then using that pattern, 3 to the minus 1 is equal to all that algebra, so we can write 3b plus 1 over a minus 2 is equal to 3 to the minus 1, which is equal to 1/3. Then just cross multiplying, we're going to get 9b plus 3 is equal to a minus 2. It's asking us to express b in terms of a, so that means we need to have b as the subject. So 9b is going to be a minus 5. So b is a minus 5 all over 9. Now the next one, this is a disguised quadratic. So we just look at this first term here. 2 to the 2x plus 5, we can write that as times 2 to the 5, because the rules of indices would mean that you'd have to add them up, and then that would get you to this first term. 2 to the power 5 is 32, so we can write that first term as 32 times 2 to the x all squared, splitting the 2 to the 2x, writing them in brackets here. These two, using the rules of indices, would mean that you would times them together and get back to that 2x. So it's 32 2 to the x all squared minus 7 times 2 to the x is equal to 0. So if we say that let y equal 2 to the x, this is the same as 32y squared minus 7y. So this is why we've got it in a disguised quadratic. So then just factorising out a y, you're going to get y into 32y minus 7 is equal to 0. So y is equal to 0, or y is equal to 7 over 32. Now what was y? Y was 2 to the x. So 2 to the x is equal to 0, or 2 to the x is equal to 7 over 32. Now 2 to the x, that is always above the x-axis, so that's a non-solution. And then here, just rearranging and writing it in terms of a log, log to base 2 of 7 over 32 is equal to x. And if you put that on your calculator, you're going to get that x is equal to minus 2.19 to 2 decimal places, and that's what it's asking you to give. Here's another exam question to have a go at. So part 1, using logarithms to solve this. You've got 8 to the 2x plus 1. Now instead of writing plus 1, we can times that by 8 to the 1, and then that would cause you to add those indices 2x plus 1 to give you that single power is equal to 24. Now dividing by 8 on both sides, 8 to the 2x will equal 3, and then undoing and writing that in terms of logs, log to base 8 of 3 is equal to 2x, so 8 to the 2x is equal to 3, so x is equal to half log to base 8 of 3. And if you put that in your calculator, you will get that x is equal to 0.264. Part 2, we can see we've got base 2 on all of these terms, but what you need to do is take that 2 up first, so it'd be log to base 2 of 11y minus 3 minus log to base 2 of 3 minus log to base 2 of y squared. Now because these are both take away, you can divide, so it's log to base 2 of 11y minus 3 divided by 3y squared, and that's equal to 1. Equal to 1, and then using that pattern, 2 to the power 1 is equal to all that algebra, so 11y minus 3 over 3y squared is equal to 2 to the 1, which is 2. Then just cross multiply, 11y minus 3 is equal to 6y squared. Everything to one side and solve the quadratic. 6y squared minus 11y plus 3 is equal to 0. 0 is equal to 2 brackets, and if we need 2y and 3y, and then timesing to get 3, we'll have 3y minus 1 and minus 3, and then that will give us minus 2 and minus 9 to give us the minus 11 in the middle. So y is equal to 3 over 2, or y is equal to 1/3. Thank you so much for watching. If you're still with me at this point, we've had a good look through at the AS Pure syllabus, all things to do with logs and exponentials. Hopefully you found this video useful. Do like and subscribe. Keep an eye out for more videos in the series, and I will see you on the next one.